Hey everyone, I'm Pavi, and welcome to pv0 to Hero, a brief history of the consensus protocol. So today I'm going to be talking a little bit about Raft, which is a popular consensus algorithm for distributed systems, and then I'm going to be talking a little bit about MongoDB's replication system, since I'm on the replication team, sort of like where we started, how we improved on Raft to sort of fit our needs as a distributed database. So yeah. So a little bit about me, I guess. I already had a very nice intro, but those were, if I had to pick three things to say about me today, those are the three things that I would have said, so go blue. Coming out of school, I really wanted I really didn't like doing like web stuff in school, and sort of like I hated it so much. I would much rather preferred working in C++. Lucky for me, at the University of Michigan, that was our entire curriculum. And out of college, I really wanted to work for a company that sort of had a balance between theoretical and practical work, and I found the perfect balance at MongoDB for me. I really like that it's sort of a product built by engineers, like for engineers, and since we take engineering very seriously, we have a continued commitment to making our system better, even if something is already working. And I think that shows through us going to research in industry and stuff and trying to incorporate that into our engineering systems, which I think is great. So the title of this talk, pv0 to Hero. What even is pv0? pv0 stands for Protocol Version 0, which is our original consensus protocol, and it was basically written by this one engineer named Dwight during the early MongoDB days, and he basically just wrote this entire thing because we needed a consensus algorithm, being a distributed database, and it was actually this algorithm preceded Raft, first of all, but it was very, very close to something that is generally accepted in industry today, and the fact that this one engineer wrote something so complicated and almost correct was pretty awesome, and is a testament to the type of engineers that we have at the company. But this talk will mostly be going over Raft as a foundation in distributed algorithms, and then pv1, protocol version 1, because that's our current replication system. So this is a meme that I made. If anyone has seen Hercules, I can try to explain it. pv0 is young Hercules. You know, he starts out, great guy, he's great, he's very nice. But then Raft comes in as the muses, and they basically uncover his true potential, and he turns into the Hercules we all know and love, which is pv1. So yeah, let's start from the beginning. Obviously, you guys are at a MongoDB World conference, so I assume you know what these terms mean, but for clarity's sake, let's just go through it again. MongoDB is a non-relational database that stores data in collections of JSON objects, and we call them documents. We maintain them in replica sets, which look something like this. The P stands for primary, and S stands for secondary, and that's me, your client. I will write and read to the primary, and then it's basically a group of MongoDB processes that maintain the same data. So this provides redundancy and high availability, which basically just means we can access our data when we need to, even if something goes wrong. Now, this is a steady state application, which means everyone is happy, everyone is up, and everyone is replicating properly. Unfortunately, in the real world, things happen that sometimes can be out of our control, and data centers go down, Amazon. Networks are slow, which can cause a lot of latency, and sometimes even you have typos, human errors, also Amazon, whatever. But yeah, so we'll be going into how we can deal with those problems. For example, what happens if our primary node goes down and we can no longer accept reads and writes to our system? Also, what happens during a network partition, which basically just means one of the nodes may not be aware of the other nodes in the set. Cool, that brings us to consensus in distributed systems. So what even is consensus, really? And that's basically just agreeing on something. So part of my presentation is actually going to be on this little whiteboard thing, so if y'all can't see, I'll try to draw pretty big, but y'all can't see, I would recommend maybe standing up, I don't know. So in our, let's assume we have a single node database, and we have some client up here. This client writes to our single node saying something like A equals 1, and this database is just okay, cool, A equals 1, and that's it. That's pretty cool. That's consensus. And In a one node set, it seems pretty simple. It gets harder when, you add more. So in distributed systems, a consensus algorithm determines how multiple nodes can agree on a consistent state in spite of failures. So consensus with one node is pretty easy. Consensus with many starts to get harder and harder. It's a fundamental problem in fault-tolerant distributed systems. Consensus involves multiple servers agreeing on a value, and once they reach a decision on that value, it's sort of final. And the cool thing about consensus algorithms is that they can make progress when any majority of their servers are available. And so, for example, a cluster of 5 servers can still make progress even if 2 of the servers fail, which is pretty cool. And if more servers fail, they start making progress, but they won't return an incorrect result, or they shouldn't. And they do so by, in the context of replicated state machines, which we'll go into a little bit more. So each server will have or node will have a state machine and then a log, and as long as that log is correct, the server should be able to apply the data in that log in the same order, and everything should be fine. Cool. So this brings us to Raft, which is, again, a popular distributed consensus algorithm, and it was originally designed to be easier to understand than Paxos, which is another common consensus algorithm. That Raft paper that is linked is the Raft paper. It's super readable. Even if you've never read a paper before, I recommend reading it if you're at all interested in any of this stuff. And some of the examples in this talk are adapted from some of the visualizations that are mentioned in the Raft paper. Cool. So we'll be going over things like leader elections, timeouts, log replication, and throughout the entire talk kind of be talking about safety to make sure we're doing correct things. So leader elections. Before we start with that, let's talk states. Not these kind of states. This is the only joke in my entire presentation, so I'd really appreciate some sort of pity laugh. Thank you. Wow, so nice. I'm also from New Jersey, so I feel like I can trash my own state. But anyway, I mean these states: follower, leader, and candidate. So a lot of Raft involves how does one node move from one state to another. And in Raft, the most common way to do so is through an election or a side effect of an election. But before we go through an election, there are some terms that I'd like to define so I make sure that everyone's on the same page. First, heartbeats. So heartbeats are basically the way that leaders can communicate with the follower nodes and make sure everyone is alive. Heartbeats are essentially an empty append entries remote procedure call. And an append entries RPC is basically just used when a leader has new entries and wants to replicate it to its followers. And if a leader has no new entries, it's an empty call. So that's what's considered a heartbeat. Next is terms, which is essentially Raft's concept of time. Time is divided into these things called terms, and each term begins with an election. They're monotonically increasing, which means you can never have terms going backwards or stuff like that. And each node stores the current term, which they exchange when they communicate with each other. Cool. And the last thing is timeouts. So timeouts is the amount of time a follower node will wait before running or starting an election. And these timeouts in Raft are randomized between 150 and 300 milliseconds. So if a follower node doesn't receive a heartbeat from its leader in this interval, it will run for an election to try to be the leader of that group. Okay, just kidding. So now we can actually go through an example of a regular election where things go smoothly and nothing bad really happens. So we're going to start in term 0 as the default. And we have our 3 nodes, all of which start in a follower state. And now since they all start in a follower state, and this is actually just the beginning of this replica set, they will time out. And since the timeouts are randomized, we're just going to pick a random one whose election timeout times out. Let's say it's this one. Goes through the timeout, we'll call it 1 millisecond. That's pretty fast. But it's going to turn into a candidate and then increase the term that we're in to 1. And it'll send these vote requests to the other two followers in the set, and then wait for a response, which is either a yes or no, for its candidacy. So the follower, it'll also immediately vote yes for itself, because why not? So it already has one yes when it's like running for an election, essentially. And so a lot of the things in Raft are based in like having a majority of the set agree to do something. So obviously in a 3-node set, the majority is 2 out of 3. So this node actually only needs one of these other nodes to vote yes before it becomes a leader. And followers generally will vote yes for the first vote request that it gets, as long as the candidate is at least as up to date in terms of data as they are. So let's say this one also votes yes, this gets 2, and then this node essentially becomes the leader. And yay, we have an elected leader and everyone seems to be healthy. So that's a very like simple example of how an election goes, you know, assuming that like nothing bad happens. So what happens when a leader goes down, actually? So say we have our leader node. And 2 followers, something like that. So if this node goes down, let's say we're in term 1 at this point. So from here, again, the timeout will again kick in with like one of these followers, and then they will essentially run for an election. And since the majority, in this case is also 2 nodes, it already has 1 yes vote, and then it'll just have this follower also say yes, and then it'll become leader again. And this leader can also start to accept rights from a client and keep this steady state going until this node comes back up. Cool. So, So timeouts are randomized, but it's rare in Raft, but it's still possible that 2 nodes can become a candidate at the same time. So basically what happens in that case if they become candidates simultaneously? In this case, it causes something that we call a split vote. So with that example, this more easily manifests in an even node set, so that's kind of what I'll be going over. So yeah, say we have like an even node set of 4 followers, and then let's say that these 2 followers have the same exact election timeout. So then they both time out in like 2 seconds. They'll immediately vote for themselves. So they have 1 vote each. And then they'll send requests to the other 3 nodes. And since each node can only vote once per term, these nodes can no longer vote for each other. They also voted for themselves. And then what'll likely happen is that these 2 followers will give their vote to different followers, meaning that these 2 have 2 votes each, and no one wins the election. This basically means no one can be a leader, and the only way to solve this in Raft is to rerun for an election. So that can cause some like term inflation and just, I don't know, increase the time in which there is no leader of the set. But Raft sort of mitigates that by having the timeouts be so randomized and having each node pick a new timeout every time. So it doesn't happen very often. Cool. So let's go to log replication. So like once we actually have a leader, we need to replicate the changes that we have made to our system of nodes. And since Raft is like a leader-based algorithm, it's the responsibility of the leader to propagate these changes to the rest of its followers. Oh, just kidding. Okay, so another example. I always forget what my next slide is. So say we have a healthy application with a leader, and we have some client that writes something to the leader saying like A = 1. At this point, this write is not committed whatsoever at all. It's just something that we told the leader, and the leader will subsequently send request to the followers saying like, hey, I got this thing that like a equals 1. Every node has this concept of a log. And it's important that these logs stay consistent or like are correct, because anytime that a node needs to go back to it, we want this to be like our state of truth. So the leader records this a equals 1 in their log, still not committed, and then tells its followers to also record a equals 1 at the same index. And then once a majority of the nodes have committed this or written it down in their logs, they send a reply to the leader saying like, hey, I did this thing. And if a majority of them have committed it, then the leader finally commits this and then tells the followers to commit it. They do that. And then finally, the leader applies this to the database and then sends a reply back to the client being like, hey, it's committed and it's all good and ready to go. And once things in Raft are committed, they are like committed forever. That is the truth. Cool. So what happens during a network partition? That's sort of like the second thing that we were talking about. And for this example, we'll sort of use a 5-node replica set to, cool. Let's say we have a leader and 4 followers here. And let's say that our client wrote something, a equals 1, again. I love A's and 1s. Cool, yeah. So let's say at this point, everyone has committed a equals 1 in their logs. But let's say at this point, there's a network partition between these 5 nodes so that these 2 nodes are aware of each other but not aware of these 3, and these 3 nodes are aware of each other but not aware of these 2. So essentially, this set will stop making progress because they can no longer communicate to a majority of the nodes in this set. But this set essentially can still make progress because they have 3 nodes to work with. So essentially what's going to happen here, let's say everyone started in term 0. What's going to happen here is someone here is going to run for an election and go through the same election protocol. Okay, actually, this term 0 is for these 2 nodes. And then these nodes here will be in term 1. And then let's say this middle one gets elected leader through the same election protocol. And this leader gets a write from a client saying something like A equals 3. This change propagates because it has 3 of the nodes in the set. And these all have A equals 3. But what happens if this client up here says something like, hey, the second entry is like A equals 4? Since this node, this leader, cannot reach a majority of the set, this change is not actually committed yet. They'll just sort of have it in their logs. So if we heal this network partition, I usually do this on the whiteboard so I can erase it, but like, just imagine it's gone. So after that happens, the leaders will communicate with the other nodes via like a heartbeat. And once this leader, which is in term 0, is aware of this leader, who is in term 1, it will step down because it realizes that the term number is lower, and basically find the last common point between its logs and the leader's logs, which would be A equals 1 here, and then re-replicate all the missed committed data until then, which would, in this case, would just be A equals 3. So this would actually take that out and then make it A equals 3. And then, we're back to having everyone consistent. This follower will do the same thing that the leader did. Yeah, and then that leader will change to a follower. Cool. So yeah, most consensus algorithms can still make progress when a majority of the nodes are still alive or available. Cool, yay! That's a high level, very, very high level overview of Raft. If you're at all interested in any of the examples we went through, or like knowing a little bit more about the implementation or like the thoughts behind the algorithm, I highly, highly recommend reading the paper. it's meant to be digestible and like much more easy to understand than Paxos. But yeah, so it works, and it works pretty well. But we thought at MongoDB, we were like, oh, can we make it work better? Since we already have the bare bones of it like already working, can we add more things to it to make it better suited for our needs? And we thought, yeah, maybe. I think so. So there are some key similarities between our replication system and Raft. One is that they're both leader-based systems. They're both log-based systems, which again just means like keeping a log consistent so that all nodes can replicate from the same log and have the same data. We both use heartbeats, and we both have this concept of elections in order to become the leader. Cool. But there are some key differences that I'd like to go over. So MongoDB's replication system is an apply first, then replicate algorithm. We have this, so that allows us to bring in this concept of like write concern and read concern. It's a pull-based algorithm versus a push-based algorithm, which allows us to do stuff like change replication. And we also have stuff like arbiters and priorities. Cool. So apply first, then replicate, which basically just means, so in Raft, what happens is when a client writes something to the leader then propagates the change to its followers first, and then gets it back, and then returns something to the client being like, oh, this change is committed. What we do at Mongo is that our primary accepts the write and immediately applies it to the database so that they can return something to the client, which is essentially a W1. Which sends a W1 reply to the client, which basically just means, hey, like this write has been propagated to one of our nodes, which is the primary. And if you use a certain read concern, in this case local, you are actually able to read that write, even though you know it has only been applied to one node. So yeah, write concern again is how many nodes have acknowledged a write. And with read concern, you can control the recency, consistency, and isolation level of the data that you want to read. So you can use write concern 1 and read concern local. Read concern local will read majority committed writes, and just one committed writes. But we recommend you use something like read concern majority or write concern majority and read concern majority so that you're not reading data that can potentially be rolled back. But if you want, you can play around with the read concern and write concern to something that fits your application. So if you want, like by adjusting the levels of consistency and availability, you can have stronger consistency guarantees, or you can loosen those consistency requirements to provide higher availability. And it basically just like comes down to what you want in your application. It's a pull-based algorithm versus a push-based algorithm, which allows for something that we call chained replication, which is the default form of replication in MongoDB. It basically just occurs when a secondary member replicates from another secondary and doesn't have to replicate from the leader, or the primary. So if a secondary picks its primary target or replication target based on the ping time and tries to pick someone that is the closest to it, that member can be another secondary, and it can actually reduce the load on the primary, which is like kind of nice. So this is what replication looks like in Raft, with the primary sort of coming down to the two secondaries. And this is what it'll look like in a typical replication looks like in MongoDB, with the secondaries pulling information. And this is sort of what it looks like with chaining. It becomes sort of this like linear progression. There's this thing we call like configurable election timeouts, which was introduced with with pv1. So this defaults to 10 seconds, and you can either increase it or decrease it depending on what you want. So higher values will result in slower failovers, but it's not as sensitive to primary nodes or networks that are slower, whereas lower values will result in like a faster failover, but you get into this thing where if the primary network is pretty slow, then you're consistently electing like a new primary and stuff. So this is in the case that like if you have a flaky network where the connectivity breaks down, is then restored and then like breaks down again and then keeps going on and off, you increase the likelihood of like flip-flopping between your leaders. So in this case, if your leader is otherwise healthy, you would want to keep this leader for as long as possible. So you decrease the time in which your other nodes are trying to catch up. So in that case, you could set your election timeout to sort of be like the average time that your network goes down to sort of like mitigate for stuff like that. And yeah. Oh, I also wrote this stuff down. Cool. Yeah, and the last thing I'll be talking about are priorities. So priorities contributes to this idea of like leader stickiness, which is basically like when we want a certain leader to be a consistent primary for the set. You can set the priority of any node in a set to like numbers, which look something like this. So priority of 0 is the lowest priority, and you're essentially just saying that you don't want this node to ever become primary, because priority 0 nodes cannot become primary. They will not run for an election, ever. But say you have a node that is in your primary data center, or you have a node with like really good hardware and you know it's pretty reliable, you would want to maybe set that as the highest priority to make sure that it has the higher chance of becoming the primary. Since priority 0 nodes can't actually initiate an election or stuff. So yeah, if you deploy a replica set across like 2 data centers, A and B, and you want to ensure like the primary node is in data center A, you just have that as like P2. If you do this, you just want to make sure that you have a majority of like the quorum is essentially what you call like people like how much of a vote that you need. You essentially want to make sure a majority of your nodes live in that data center as well, so that you will not end up in a situation where you don't have a primary anymore. So yeah, I think that might be it. Okay, cool. I brought you back to the meme. Hopefully this makes a little bit more sense now, how we, like where we started with pv0, which did not have a concept of terms, and you could like veto things, which is like, but then we used like Raft to sort of like fix through those problems and like create a system that we think is like pretty robust, and yeah, is our current way of doing things. And I think that's it. Yay! Thanks so much for coming out to the talk, y'all.